So I have changed the title a little bit compared to what's written here, but you hope you don't mind. So instead of telegraph trigonometric system, we call it hyperbolic Fourier series. Fourier interpolation of the Klein-Gordon equation. So let's see. I will move forward. I think I move here, right? Ah, that's good. Okay, we take a brief review of Fourier series. Let us begin with the classical theory of Fourier series. Suppose you take a periodic function on the real line, and we assume, of course, it's not the crazy function, some function you can integrate and maybe continuous and so on. And it's periodic with period 2. And then such functions can be represented in terms of Fourier series. So these are Fourier series. That's a beautiful thing. It's you have these complex exponentials which decompose into cosines and sines. And you get these coefficients by a beautiful formula, just an integral of the function against the conjugate of these these basis functions. It's why it comes out so nicely is the fact that these complex exponentials, they form an orthonormal system in this L2 space of periodic functions. So then it's easy to realize how the expansion works. Okay, so now we come to a kind of classical problem. It's great for two periodic functions. But what if you want to consider other functions that are not two periodic, maybe three periodic? Well, if I say three periodic, then you say, okay, just replace 2 by 3 and do some trivial adjustments, and it works. But suppose they are not even periodic, then what do you do? Well, the classical answer has been to allow more general frequencies, and this gives you, well, for instance, Harald Bohr's theory of almost periodic functions, or alternatively, the theory of Fourier integrals of L2 functions on the real line. Okay? So there are many ways to think about this. Let me suggest to you an alternative system which seems a little counterintuitive at the start, but then when you think more about it, you see the beauty of it. So let's just say, okay, we keep those basis functions that we started with, and then we add on a few more. Which ones? We do these. So we just change from t to -1/t. So what do these functions look like? Maybe I can try to draw them. Okay, so if a sine function with period 2, it will look like this. Then this is like sine x. Sine. Pi x or something. If you try to think about sine of pi over x, then we remember that this is one of these crazy functions at the origin. They jump up and down. But out here, far out, if this is 0, then it looks good, but then it's got this infinitely many ups and downs, and from here it comes the same way. Okay? It is not perfect illustration, but I try to give you the feeling of it. So what I want to say is that these sine functions, they're good at describing what's happening on the period. You expand the frequencies and you get more and more. Instead here, it will be the fact somehow that, okay, if I draw it like this, I draw one period -1 to 1 here. Then over here it will be, you could think like this, maybe it's, okay, it could be like that, maybe. So it's like -1 and 1 there. And so using those sine functions could be good. Sine with 1 over x is that since this interval can be represented by sine pi n x, then correspondingly here we could represent outside. Because the interval is by 1 over x becomes the exterior interval instead. Okay. So now the trouble, of course, is that, okay, we do get the garbage from periodic extensions. So we have to adjust for the working with this basis and this other basis outside, but then there's a mixture of the two effects. Now, you could, of course, say, okay, we work with just these complex exponentials in one sense and the other sense, but it's better to to use characteristic functions to kill off and just localize. But we don't want to do that. So we accept these, the mixture of effects, that they influence each other. Okay, so what would be a possible expansion? So with not assuming anything about, well, about periodicity, just take any function which is sort of reasonable, bounded, let's say, or something like that. Bounded measurable function. You'd like to represent it in such a way. A first series and then a second series. And to avoid double counting, there's one double counting possibility here, that we have constants coming from the first system and constants coming from the second system. So we just don't want to have both constants coming from both sources. So we can kill one of them. For instance, the B0 could be 0. And then you could wonder about, okay, yeah, that's our tentative thing. Maybe it's possible. And then, and this representation, type of representation, we would call.
for now? It's already in some L2 space?
Yeah, well, you don't have to assume. I don't assume that the convergence is strong pointwise or anything. I just think that maybe it's possible in some weaker sense. The convergence could be in the sense of distribution theory, for instance. I don't mind. Okay, so that's what I would call hyperbolic Fourier series. Hyperbolic because, well, there's two reasons for it. One reason is just that, well, 1 over t, if you draw it, it's a hyperbola. And there was another reason for it as well, which we'll come to later. Then I just want to give you an interpretation in terms of the wave equation first. So how does that work? Then you can think of, separate the two. You get two, you can say you can work with a sum of two periodic waves. So you take a wave equation on a torus, okay? And such things would be, I mean, depend on how you write the wave equation, but one way maybe in simplified coordinates, you would say it's function depending on one variable plus function depending on the other variable. Okay? So we have a function depending on the variable r, a function depending on variable s. Okay, and both periodic, and then you want because of this representation, it solves this wave equation, and then the expansion corresponds to looking at such wave solutions on a hyperbola. And the hypothesis would be that you can recover any function in such a way. Restricting such a hyperbolic wave solution to the wave equation on this hyperbola doesn't really amount to any strong restriction on the given function. Okay? Now we come to the Klein-Gordon equation. The Klein-Gordon is a friend of the wave equation, but it's not exactly the same equation. You can say that it's a wave equation if the lambda is 0, but you have some non-trivial lambda, then it's just the eigenvalue problem for the wave operator. And we can then assume that our lambda is 1, and we then talk about these solutions that look like that. Partial derivative with respect to x, partial derivative with respect to y of the function is equal to the function. The function is unperturbed by such differentiations. Now, when you think of it, you start to try to conjure up such functions, you realize that, in fact, there are such solutions. Like this u sub tau there. Take it for any complex number, non-zero number, and take the derivative in this way, and you have a solution. On the other hand, unless tau is real, this kind of expression grows strongly in some directions. So you need tau to be real to have a kind of standing wave. Okay, something that doesn't blow up exponentially. Okay, and then based on those basic solutions, exponential solutions, we can write a more general solution using a measure, integrating over over tau. Over our parameter tau. Okay? And we call those functions canonical telegraph functions here, but maybe, maybe just canonical solutions to the Klein-Gordon equation would be more reasonable. Okay? It doesn't mean that all solutions to the Klein-Gordon equation are like that, but there are some reasonable solutions of that form. Next. We would, at least for such a representation of any function, you'd like to know that, in fact, you have enough functions in there to represent anything. So how to test it? Well, you can test it by duality. You say, let's look for a function and assume that it annihilates as a functional those two bounded functions on the line. Now, if this forces G to be 0, then our system is at least weak start complete in the spatial infinity of bounded functions. Next, what can we do? We use this G to form a function u, capital U, of two variables, which solves this Klein-Gordon equation. Now, the assumption, what does it mean for the function u of two variables? Let's look at it. This function, u, must then vanish on on what I would call a lattice cross. I can draw it for you. Okay? So that Klein-Gordon equation, solution to the Klein-Gordon equation would have to vanish on those points. So the question is, a natural question now is that if that forces the function, the original function to vanish, which means that the Kepler function u has to vanish. So is this a uniqueness configuration of zeros for solutions of this form of the Klein-Gordon equation? Now, if you know anything about elliptic equations, you know that for elliptic equations, you get some density criteria often of uniqueness and so on, like if you deal with holomorphic function and boundedness and so on, you get some very good criteria. Now, with some stretch, maybe you could go to parabolic equations. But how could you expect anything like this to happen for hyperbolic equations? Hyperbolic are just crazy equations. They not no ellipticity at all. Nothing. No regularity is forced. So why would it be true? Okay. So I try to create some doubts in your minds. Some doubts in your minds. But nevertheless, it is still true. So this system is weak star complete in L infinity. And I already alluded to some reasons earlier why it could be true, because the functions, one system works well outside this interval -1 to 1, and the other system works well inside the interval. So maybe together they're able to represent everything. There is some hope there. Was some hope. Okay, let's keep at it. I'll tell you something about the proof of that theorem. How does it work? We start with some function which is periodic. And then we know that such periodic functions can be expanded into complex exponentials using Fourier series. And then we would get from the assumptions, we would know this thing, that the integral of f against this given function g must be 0 for any such periodic function. But also the other thing, that if I plug in f of -1 over x, it would be the same, also 0. So that's what we would know. But why does that force g to be 0? Well, we can do some observations, preliminary observations. We can define for a given integrable function, we can do what might be called the periodization. What is the periodization? You take an L1 function of the line, you shuffle it by 2 units here and there, back and forth, to cover all the even integers translates, and add them up. Then, after some thinking, you realize that that function must be periodic. Of course, it could be a bad function that it blows up, but it doesn't. Because if you start with an L1 function on the line, this is an L1 function on the interval -1 to 1. Now let's look at this operator pi2. Then pi2, what does it do? It shuffles an integral against this function f on the interval -1 on the reals this integral to the right-hand side, you can shuffle it to an integral on the interval -1 to 1 instead. And then what happens if the first condition is that it turns out to be the fact that pi2 of g has to be 0. But that's of course not enough to force g to be 0. But the additional thing is that we introduce j1, which is a transformation on L1, which is isometric. Okay, it's just a change of variables times the Jacobian. So it's an isometry on L1. The additional information we get from the two systems together is that first this pi2 of g is 0, and then pi2 of j1 g is 0. Okay? Okay, that's what we know. But how to deduce that the function g is 0? Maybe it isn't. So what we do is we split the pi2 into two pieces. Identity map plus the sum over all the other ends. Okay? So we remember that pi2 was the sum over all ends which were overall integers n. And now we single out the 0 and n equals 0 and says, okay, that's special. We keep it. And the other sum we keep as a sum. Okay, nothing really to it, but okay. Now, next we observe that, well, knowing the function h on the complement, the outside of the interval -1 to 1, determines that complementary pi2. Because the shufflings move you outside the interval -1 to 1. Okay? And now the equation could be written like this. G is equal to minus pi2 cross of G, and the other one like this. Okay? We can now try to mix these information and hope that it will give us something of value. For instance, we can say, okay, we implement this fact into, we can apply J1, for instance, on both sides. So J1 is idempotent. You apply it twice, you get back your function. So then we just apply J1, and we have this equation. So we have these two equations. We try to combine them, but still they're separate at the moment. So you could think of it as a system of two fixed point equations. We have one transformation here, minus pi2 cross. You look for a fixed point for that transformation. And again, it should be at the same time, you look simultaneous fixed point for that operator. All right. And then we combine these two equations. For instance, we can we can get these equations 11 by the two possible combinations. And well, okay, we can interpret the first equation as an equation concerning this function on the exterior interval, exterior of the interval, and the other one concerns the interval itself. And for simplicity, we prefer to work with the second equation. In fact, they're kind of equivalent. So working with one, it tells you how to work with the other. So, and now we can just introduce a notation called L1, this pi2 cross applied to J1 operator, then we get this formula. This formula, if you are trained with some dynamics, you start to realize that this formula is has the form of a transfer operator. Now, if we interpret L1, what does it do? In terms of the second equation, it just says that G is equal to L1 times L1 of G. So it's a fixed point equation for L1 squared. This one. In other words, if you look at it like this, I minus L1 squared, that should be 0. On the other hand, we can factor it like this. And they are both commutative. And so using that, this helps you to look for eigenfunctions of L1 with eigenvalues plus or minus 1. If there are any. Okay. And now you can split if you like, and you just need to study the dynamics, in fact. So the dynamics has to do with the Gauss map, or a version of the Gauss map, which has to do with the even partial fraction expansion. It has been studied. It's known how these iterates behave. And the main fact here is that the iterates, if you iterate in the dynamics of this minus 1 over x fraction apart, modulo 2 of minus 1 over x, then it's rather random, of course, but it has this quality that the point minus 1 and 1 are kind of the same, and they are weakly repelling. They repel, maybe not attract, but they don't repel strongly enough. So if you look at iterates of a typical point, generic point, they will spend a long, long time near these two endpoints. In terms of invariant measure, it means that the invariant measure is not finite. It would concentrate. It has infinite mass in the neighborhood of plus minus 1. And in fact, it's known what is the invariant measure. It's 1 over 1 minus x squared. But it's ergodic apart from that. So it means that you can use the ergodic theory of infinite mass. Anyway, this is enough to prove that there are no eigenfunctions in L1. Okay? Let's look at this expansion theorem from another point of view. And we hope now we can compute these coefficients somehow. And we can split this. Notice we can split it into sum over positive and negative coefficients. There are two series, and you split each one, so you get 4 terms. This term is holomorphic and bounded in the upper half plane, more or less. Maybe not exactly, but it is not at least not exponentially growing. It may be a bit bad as you approach the real line. This one is conjugate holomorphic in the same way, but it's also bounded. Here, this one is holomorphic also, and bounded. And then this one is conjugate holomorphic. So now we try to split our function into two pieces. So one piece is the holomorphic part, and the other piece is the conjugate holomorphic part. Okay. And this is like the standard splitting of harmonic functions. So you take your function on the real line, you want to extend it to the upper half plane harmonically. Okay? Usually you can do it with using the Poisson kernel. Okay? And then using for the harmonic function, you split it into analytic plus conjugate analytic. Okay? And that's how my splitting there, f plus and f minus. So in fact, I just need to deal with holomorphic functions or conjugate holomorphic functions. But they're kind of the same, so we can just look at the holomorphic functions. So we focus on the holomorphic function, the f plus. And now we need to split. We need to understand how to split it in such a form. That's the question. How do we split it? Using two Fourier series like this. Any questions? No? Did I lose you all quickly? Okay, so that's what we're dealing with these. We try to split in this way. Now, no, our given function was not periodic or anything. So f plus is also not periodic, but f plus is holomorphic and bounded in the upper f plane. So that's what we hope to be able to split it now into in such a form. And how to do it? I did this simplification. It's not really needed anymore. I understood how to not do it. This is even and odd. It helps sometimes to work with even and odd functions. But in fact, you don't need it, and so maybe I should just skip it. These are even and odd projections. So now it turns out that to do what I want to do, all you need is to solve a Dirichlet problem. Here in the previous presentation, I mentioned Dirichlet and Dirichlet-Neumann problems. They are actually problems that are natural also, and they come from the assumption of oddness or evenness, but actually not needed. So what is the... Okay, I didn't draw anything there, so maybe I can draw something here. Or maybe here. Okay. You notice that these 2 points, one, -1 and +1, they are important in what I'm talking about. But now I made an effort to start to split my function on the line, move it from the line to a function in the upper half plane. First I had a harmonic function, I split it into analytic and conjugate analytic functions. So I now work with a holomorphic function, f here. Holomorphic, and I call it f plus or something like that. And I need to split it into those, one that was periodic and the other one not, was periodic with respect to, after transformation, -1 over z or something. So now, what turns out to be important is this. Consider in the upper half plane the circle. The part of the circle which is in the upper half plane. Next. Next, what do? We consider those straight lines. Vertical. One more thing we need to do. We need to identify these two sides. So we actually do periodic identification. Okay? So you think of it like this, that you take this piece of paper, you cut it, you throw this away, you throw everything outside away, and you get this piece of paper. And now you fold it and glue these two straight lines together. Okay? Using Scotch or something. And then we have a cylinder. On this cylinder, we want to solve a Dirichlet problem. So we want to solve the Dirichlet problem to find the harmonic function h, which on the cylinder, such that h on this upper part of the circle is my given function f plus. Okay? So I don't care what's going on at these two straight line edges. They get glued together. The only thing that matters is the circle. Got it? There, because, okay, I'm talking about Dirichlet problem on... Can you hear me? Is working, the microphone?
Yes.
Okay. So this is a surface, and there is a point at infinity, of course, which I'm not mentioning much, but you can think of it like that you glue it together there too. So there's no opening there. You just fill it in.
It looks very, it looks like something close to the factor over, or complex plane over SL2, but not.
No, you don't work with this, just now periodic. So you could think of it like, okay, so it's a fundamental domain for, as you noticed, right?
Yeah, it is.
But you only do solution here. And these two parts are glued together. Okay? So it's a cylinder. And you can glue, fill in the point at infinity. It's just interior point 2. Okay, so we solved the Dirichlet problem. And then what? Okay. When you do it, you get, you realize you get the H harmonic. And it can be viewed as a two-periodic function. So h of z plus 2 is h of z. Yes? Next, what can we do? We can also split it. Harmonic functions, if they are two-periodic, they split into analytic and conjugate analytic functions. Yes? So h, maybe it's equal to g of z, some holomorphic function, plus, okay, g1, I'm not sure what I can call it, but g2 maybe, of z conjugate. All right? Two holomorphic functions. And both of them are periodic. So they are represented by Fourier series. Fourier series. And now there's one more trick, but I'm coming to it. Maybe I move on with the slides. Okay, so what did I do? Yeah. Okay, so what happens here is that these two functions, g1, it will be a sum n greater than or equal to 0 of some, I don't know, alpha n's, e to the I pi n x, oh z, sorry. And the same with g2, maybe beta n's. but we can keep the constants within one of them. So we just assume n bigger than 0 there. Okay, so we did that. And now we study what happens when you take conjugates. So you do write this summation alpha n e to the I pi n z plus summation, well, beta n maybe bars, e to the minus I pi n z bar. Okay, now comes the magic moment. We observe that here, if we look at the just on the unit circle, okay, so now we look at this on the circle. Just on t plus. Let's do it on t plus, hoping that everything is good. Okay? Then on t plus, on this positive part of the unit circle, in the upper half plane, we get what? We have a harmonic function there, but on that, it's also equal to what? Which function? It's equal to f plus. It solved the Dirichlet problem, right? So it's equal to f plus. And we have the series sum there, alpha n's, e to the I pi and z. But then there is another one, beta n bar, e to the minus I pi and divided by z. You see, because on the unit circle we have z bar is equal to 1 over z. Right? You see it? It's 1 over z. And that's like the series we're looking for. And not only that, f plus was holomorphic. And this guy on the right-hand side is holomorphic too. And they're equal to each other on an arc. So they must be equal everywhere. Right? Uniqueness theorem for holomorphic functions. So this holds everywhere, in the upper, wherever things are well defined. And then you have to work a little bit harder with the harmonic function, the solution to the Dirichlet problem. You need to see that it's harmonic across, and that's not hard because the data is given by a holomorphic function in the upper half plane. So you can do some Schwarzschild reflection trick here to extend. You can extend. You have lots of boundaries. You need to keep extending. And then finally, when you do it, you get a function which is harmonic in the whole upper half plane. Because you keep doing.
F plus, was it real value to complex value?
Sorry?
F plus, was it now real value to complex value?
F plus was a holomorphic function. So it was, we split the original function f, we split it, we extended harmonically, so we have a harmonic function, and we split it f plus and f minus. F plus was holomorphic, f minus was conjugate holomorphic. Okay? So that was somehow the trick. And here is a lot of work. One can control things. You can get. You need to do more. Okay. So what do we do when we do the Dirichlet problem? You immediately get a periodic solution here. Okay. So we have a periodic function. It periodically extends like this, harmonic and periodic, and then you need. But you want some function which is harmonic in the entire upper half plane. So, but you can reflect in this one, for instance. We do reflection there. And then use Schwarzschild reflection. We go here, And then we get, how does it look? I think it looks like this. Not too small. Maybe something like this. And we get extension here, harmonic extension to this. And then we need to keep at it, going deeper and deeper. Right? Okay, maybe you didn't capture exactly what I was thinking about. So, okay, I have f plus is the function, right? So I have a harmonic function in the upper f plane. I can always subtract f plus. So I get a function which is 0 here, harmonic and 0 on this circle. Now we do Schwarzschild reflection of that function. Okay? So we get another harmonic function here.
Some part of this circle, yes?
Yeah, well, in this part.
Okay.
Except for these, I think. Yeah. Isn't that how it is? Yeah, I think. Because these holes are reflected over here. So you manage to, you started here and you manage to reflect over there. But then you keep at it. You keep reflecting in these things. You subtract what you know it has to be there, etc. Get control. But it has to grow a little bit, of course. So this is the kind of estimate I was able to get in a simple way. Yeah. Okay, I hear some mention of some related problem. Perhaps it's not that important to you guys, so I think I can leave it. I could also mention radial Fourier interpolation. You take a function which is radial in Rd, in d-dimensional space. Okay, so it just means that it depends on the distance from the point to the origin. That's all. Well, a tentative Fourier interpolation formula could be like this. You take values of the radial function at certain radii and try to recover the function from those things. Okay, let's see how this, if there's a relationship here. We could try the formula on Gaussians just to get a feel for what could be happening here. When you do Gaussians, you can calculate these those integrals there very well. So to get the Fourier transform. And we see that the Fourier transform of Gaussian is a Gaussian also, except that you get a constant factor in front. And this extends to also to the complex case with Gaussians that are not like, yeah. You can work with a tau, which is just the imaginary part positive. You don't need it to be pure imaginary. Anyway, you can, what the formula would suggest is this possibility of extending Gaussians in such a way. Writing down Gaussians in such a complicated way. Yeah, and then the equation looks like this. Observe what happened here. Do you see it? Remember that before we thought of x as the variable and tau as a constant. But what if we switch our perspective? We change and we start to think maybe tau is our variable. And x is some fixed point, a point which we don't have to move too much. We can just forget about it for a moment. So then it's a matter of splitting functions into, when d is 0, it would be exactly these hyperbolic Fourier series, which I tell you about. And actually, it also works when d is 4 by a trick. And you can also, using this idea of Radchenka, it's possible to reduce to d equals 0 through other means. But it's a little tricky. Yeah. So you see, these things come very naturally. In fact, this is solving these equations was the way that Vyazovska was able to obtain her sphere packing theorem. Now you could ask, okay, we started with those functions. And they are in bounded analytic functions. And, well, a natural question, since I told you that they are, if you extend to all integers m and n, then we get a system which works, is weak star dense in L infinity. Well, what about if I just look at the holomorphic ones? The ones that are extend bounded and holomorphic to the upper F plane. Then do I fill up using linear combinations? Do I get to fill up the whole space of bounded analytic functions in the upper half plane? It turns out that this question is a little more subtle than the previous question. And what the other theorem immediately gives is this fact, that those functions would be weak star dense in the space of bounded mean oscillation, BMOA, analytic bounded mean oscillation functions. And now, in terms of the this original Klein-Gordon equation, what it amounts to is like throwing away half of the hyperbole, half of this lattice cross. Just delete this. Does it force, well, it doesn't force the function to be 0, but maybe it forces it to be 0 here, if it's 0 here on these points. That's the kind of question that appears. And we struggled with this with Alfonso. And in fact, it turns out that it is true. And it's a little more subtle than the other theory, the other thing. So what follows is if G annihilates those two collections of functions, then G is an H1 function. Meaning that it's L1 and its Poisson extension to the upper F plane is a bounded, is a holomorphic function. Okay? I can say some words about the proof. Let's see, how am I doing with time? It's finished, more or less? Or?
Yeah, we should
Round up. Round up. I can say some words about the proof we had with Alfonso. It's a little bit tricky. But anyway, there's some splitting into even odd and things like that. And then we can assume that we're dealing with a function with this kind of symmetry. And then somehow it follows, it's more subtle, it requires more careful study of the transfer operator acting on Cauchy integrals. Or if you like, also it's pretty much the same, studying how the transfer operator collaborates with the Hilbert transform. So maybe not so well, but you can squeeze it out. Here are some references. Yeah, this is my first paper with Montes Rodriguez. We were able to get a very nice result, and animals liked it, so they took it. Then there are two papers in Journal of European Math Society, and these paper by Vyazovska, Radchenka, Vyazovska paper that is published now by Publication Mat IHES. Yeah. And this is the paper where the tricky part was published. It just now appears in Journal d'analyse mathématique. Okay. So I think I should thank you for listening so patiently.
Thank you. Are there any questions or comments? So could you explain maybe a little bit more how it relates to the sphere packing problem? Sorry, I didn't quite catch it.
Yeah, it has to do with the basis functions and Fourier interpolation. So the sphere packing problem turns out to be a question of finding certain functions, and if they exist. And it turns out that they are related with this kind of problem. Interpolation problem, but it's a double interpolation problem. So what is double about it is that it involves not only the value of the function, but also the derivative at the same point. And the same for the Fourier transform. So it's a double problem. And what's important is that these functions, an and bn, that they have some property that they're like positive outside what corresponds to the radius of packing size. So that's somehow magically the appearance of such functions which have the property of being, maybe they're negative inside and positive outside or something, and all of them.
So in some sense this picture is a little bit like that, right? So some functions have to be defined for outside of the spheres, right? Or
yeah, maybe a little bit, but these little, yeah. Okay, it's the connections is not straightforward. You need to go through this kind of considerations to get from one type of problem to the other.
and in other dimensions there is no.
Why? In 24 also they were able to crack it. 8 and 24 with this method. It's a beautiful method of which goes back to, what's his name? Elkis, and Cohen and Elkis. Published around maybe 2005 or something in the Annals. They found this straightforward way to prove something if certain functions exist. But they didn't know they existed. They did numerics to show that maybe they existed, but at least they were able to get close to the critical, what was thought to be the critical packing. Okay.
Any more questions?
Yeah, maybe just one short question.
Yes.
So, if I would like to play with that, I substitute the system of exponents by another system which is dense in some sense and which can approximate any function on the interval.
Mm-hmm.
And then I also and then with each such function fn, I consider fn of z, I add a function fn of 1 over z.
Yeah.
It seems that this procedure, well, at least what is written on what is drawn on the blackboard,
Yeah.
this argument will kind of survive. Yes. No?
It will depend
It depends
on the
So
system.
It's not
Yeah.
like a general.
No,
measurement
it's
of
you have to. It's very sensitive to which.
Okay.
Because remember, I represented using my knowledge of Fourier series. I know that you can represent any periodic function using this, and so on. So it has to do with these things. And yeah, but maybe something would survive. Maybe you could. I don't know exactly what are the precise requirements that you would like to introduce. Okay.
Okay, then let's thank the speaker again.